Hello my precious friends, I really hope that you are doing great. Welcome to our today's class. It is our 7th and last lesson on the 5th topic of Form 4, which is called electromagnetic induction. As usual, let me commence by giving the quote of the day, which states that it's okay to lose, but be careful not to lose the lessons. We shall discuss that quote at the end of our class today. So today we're looking at the fourth application of electromagnetic induction, which is called alternating current generators, abbreviated as the AC generator. So remember, an alternating current generator is also called an alternator. So remember, generally, a generator is used to convert mechanical energy into electrical energy. Remember, under mechanical energy, we have two types. We have the kinetic energy, which is the energy possessed by a body in motion. We also have potential energy, which is the energy possessed by a body at rest at some height from the ground level. So let's look at the main features of an alternator or the AC generator. Of course, it has a magnet, then it has a coil, a rectangular coil which is placed within the magnetic field. Then it also has some cardboard brushes which connect it to the CRO, that is the cathode ray oscilloscope, which is used to display the waveforms of the induced EMF. Then apart from those features, the alternating current generator also has what we call the slip rings. Remember, the only structural difference between alternating current generator and direct current generator is that an alternating current generator usually has slip rings, but for the direct current generators, they have what we call commutators or split rings. So that is the only structural difference between an AC generator and a DC generator. So the difference is that AC generator has slip rings, but DC generator has split rings, or it has commutators, as we shall see later. So when the coil is in the horizontal position, the side AB and CD are cutting the magnetic lines of force. Therefore, an EMF is therefore induced in the coil, and the current flows from A to B and also from C to D. So remember, we said that a generator converts mechanical into electrical. Therefore, we are agreeing that a generator is simply a dynamo. And we said that a dynamo, when we are dealing with dynamos, we use strictly Fleming's right-hand rule. So we want to apply the Fleming's right-hand rule to determine the direction of the EMF that will be induced in this particular coil. That is the coil A, B, C, and D. So I want you to place your right-hand fingers such that the thumb is perpendicular to the first finger and also the second finger. Then let the thumb point upward, that is in the direction of the motion of this particular coil, because if this is the axis of rotation, you can see the rotation is in this direction. So when we rotate it, actually the side AB will be moving upward. The rotation is in the anti-clockwise direction. So when the coil AB is moving upward, actually the motion is upward. So I want you to, using your right hand, place the thumb in this particular direction, in the upward direction. Then of course, this is the north pole and this is the south pole of the magnet. Therefore, the magnetic field is flowing from the north pole towards the south pole. So I want you to place your first finger in the direction of the magnetic field. So let your first finger point in that direction, then of course the thumb upward. So can you observe the direction of the second finger? You realize that the second finger points downward. That is, it points in the direction of AB. So that means whenever this, that is when the side AB is moved upward, actually the thumb will be upward in the direction of motion, then the first finger will be in the direction of the magnetic field, then of course the second finger points in the direction AB, showing that the induced current will be moving from the direction A towards the direction B. Then similarly, remember, as the side AB moves upward, because remember we are rotating this particular coil in the anti-clockwise direction. So as the coil AB moves upward, actually the side DC will be moving downward, because remember this particular coil is rotating in the anti-clockwise direction. So as AB moves upward, actually the side DC will be moving downward. Therefore, I also want you to use your right hand, place the first finger, second finger, and the thumb mutually at right angles to each other or perpendicular to each other. Then, because in the side DC, the motion is actually downward of that particular side DC, I want you to place your thumb facing downward. Remember, we are strictly using the right hand. Then of course the direction of the magnetic field does not change, is from the right hand direction towards the left hand direction. So let your first finger point towards the left hand direction, of course with the thumb pointing downward. So when you do that, you realize that the second finger is actually pointing upward, or in that particular the direction of C towards D. So that simply means that in the first rotation the current is flowing in the direction AB, then from C to D. So this is the actually the direction of flow of that particular current. It is flowing from A to B, then it is proceeding from C actually to D. So when the coil is in the horizontal position, the side AB and DC are cutting the magnetic lines of force. You can also see that the lines of force are actually moving in this direction. So when the coil is in the horizontal position, then this particular coil is meeting with these lines of force at an angle of 90. So can you check this angle, the angle between the coil and actually this magnetic field line? So the angle is 90 degrees. And we said that whenever a conductor meets the magnetic field lines at an angle of 90 degrees, then we are going to have an EMF being induced in that particular conductor. That's why we are saying that when the coil is in the horizontal position, because in the horizontal position it is meeting with the magnetic field lines at an angle of 90, the side AB and CD are cutting the magnetic lines of force. Therefore, an EMF is therefore induced in the coil, and the current flows from A to B, and then of course from C to D when you apply the Fleming's right hand rule. Then when the coil is in the vertical position, remember in the vertical position, that simply means that the side CD will actually be up, then of course the side AB will be downward. So when that happens, it simply means that your coil or the sides AB and DC are actually parallel to the direction of motion of the magnetic field lines. Then we said that whenever the conductor is parallel to the magnetic field lines, then that means the conductor is not cutting the magnetic field lines. Therefore, we don't expect any EMF to be induced. So when the coil is in the vertical position, the sides AB and CD are moving parallel to the magnetic lines of force. So in the vertical position, the side AB actually moves up, then the side DC moves downward. Therefore, they are simply parallel to the direction of motion of the magnetic field line. So in that case, hence they are not cutting the magnetic field lines, and in that case, when that is the magnetic field lines are not being cut by the conductor, then the EMF induced will actually be zero. So that is why the EMF, that is the induced EMF, drops to zero and the current stops actually flowing. So during the second quarter rotation, so the second quarter rotation is when the side AB has actually gone to the side CD, and when the side CD actually moves to the side of AB. So during the second quarter rotation, the coils start cutting the lines of force, and the induced EMF increases from 0 to the maximum value when the coil is again in the horizontal position. So the current now in this particular case flows in the opposite direction, i.e. that is from B to A and then from D to C. Remember, during the second quarter rotation, the side CD has actually come to the side of AC. So D replaces A, then of course C replaces B. Then on the other hand, the side A will actually replace D, then the side B, of course, will replace the side C. So when we are in that position, so remember in this direction, B is now here, that is during the first quarter rotation, the side B is here, then the side A is actually here. And remember in this particular case, the current will be flowing upward, that is from the side B towards the side A, which has actually rotated in that particular direction. So that is why we are saying that the current flows from B to A. Then because the side DC has actually, D has replaced A, then C has now replaced B, then on this side, the current was actually flowing downward. It simply means that on this side, the current will be flowing from D towards C. So you can see that is why the current flows from B to A, then of course from D to C. That is whenever you apply the Fleming's right hand rule. So you can see that this direction is actually opposite to the initial direction. The initial direction was from A to B, then C to D. Then this direction is now from B to A, then D to C. So actually the direction of flow of the induced current is opposite, or it has changed, and that is why you are seeing we are having a graph which is on the positive side, then it changes to the negative side, positive side to the negative side, that way. So the purpose of the carbon brushes, they simply give connection to the external circuit. The external circuit in this case, of course, is the CRO, or the cathode ray oscilloscope, which displays the waveforms of the induced EMF. So the output EMF displayed on the CRO is actually sinusoidal, that is in the form of a sine wave as shown in this particular diagram. So this is a graph of the induced EMF against the angle at which this particular conductor is meeting the magnetic field lines. Remember, when the angle between the magnetic field lines and the conductor is 90 degrees, then maximum EMF will be induced. That is at this particular position. Whenever the conductor is vertical, or whenever the conductor is parallel to the magnetic field lines, no EMF is induced. That is when we are at this particular position. Then during the second quarter rotation, now the current will flow but in the opposite direction. So the current will be induced but in the direction of BA to DC. That is why you are seeing our graph is going to in the negative direction of the EMF actually axis. So this is during the second rotation. Actually the current is induced but in the opposite direction. So you can see the current is alternating from the positive direction to the negative direction. Again, during the other, that is the next rotation, the current will be induced but in the positive direction. So because the current is alternating from positive to negative direction and back, that is why this type of generator is called an alternator or an AC generator. That is an alternating current generator. So the key thing here is to know how to determine the direction of the induced EMF. You simply apply the Fleming's right hand rule. You ensure that your thumb is pointing in the direction of the motion, the first finger in the direction of the magnetic field, then the second finger will always point in the direction of motion of the induced current. So for example, if you are told to give the direction of the induced current in the first type of rotation of that particular conductor, then the direction will be from A to B, then C to D. So A, B, C, then to D. Next. The fifth application of electromagnetic induction is in direct current generators, which are abbreviated as the DC generators. Remember, the only structural difference between AC generators and DC generators is that for the case of AC generators, they had what we call the slip rings, but for the case of DC generators, they have what we call the split rings, which are also called the commutators. So just like the AC generators, the DC generators also have what we call the carbon brushes, which sometimes we can also use what we call the graphite brushes because they function in the same way. So remember, a DC generator is still a generator, meaning that it also converts mechanical energy into electrical energy. Therefore, it is actually what we call a dynamo, and we shall be using what we call the dynamo rule, or what we call the Fleming's right hand rule. Remember, it is only in motors which convert the Remember, motors will convert the electrical energy into mechanical energy. We said in motors, that is where I used the Fleming's left-hand rule, which was also called the motor rule. But in dynamos, which convert the mechanical energy into electrical energy, we strictly use the dynamo rule or the Fleming's right-hand rule. So when the coil is in the horizontal position, the sides AB and CD are cutting the magnetic field lines of force. So you can see the side AB is actually meeting with the magnetic field line at an angle of 90. Similarly, the side DC is also meeting the magnetic field lines at an angle of 90. Actually, this angle is about 90 degrees. So whenever a conductor meets with the magnetic field lines at an angle of 90, then we expect some EMF to be induced in that particular conductor or in that particular coil. So that is why when the coil is in the horizontal position, the sides AB and CD will be cutting the magnetic field lines. Therefore, an EMF is therefore induced in the coil. So the current flows from A to B, and also from C to D, of course, as predicted using the Fleming's right hand rule, or what we call the dynamo rule. So I want you to take your right hand, then ensure that the first two fingers and your thumb are mutually perpendicular to each other. So because when the coil is rotating in the anti-clockwise direction, actually the side AB will be moving upward, when the side DC will actually be moving downward in order for the coil to rotate in the anti-clockwise direction. So when the side AB is moving upward, I want you to place your thumb pointing upward according to this direction. Then of course the magnetic field will always move from the north pole towards the south pole. So you point your first finger in from the right hand direction towards the left hand direction. Then I want you to observe the direction of your second finger. So you realize that your second finger is actually pointing out of the paper or along the direction of AB. So that simply predicts that the induced current or the induced EMF will be moving from point A towards point B. So the direction of motion of current in this side will be from A towards B. Similarly, I also want us to apply the Fleming's right hand rule on this other side. Now, the side DC will actually be moving downward. That is when we rotate the coil in the anti-clockwise direction. So DC is moving downward. So can you place the thumb of your right hand pointing downward? Then of course the first finger should be pointing from the north, that is from the right towards the left, because the magnetic fields have not actually changed. So the magnetic fields are still pointing from the right hand direction towards the left hand direction. So point your thumb downward, then of course the first finger in the direction of the magnetic field. So now observe the direction of your second finger. You realize that your second finger is pointing into the paper or along the direction of C and D. So that means that the induced EMF or the induced current will be moving from C to actually D. Therefore, the overall movement of the current in this particular coil will be from A to B, then C towards D. Remember, if you interchange the direction of rotating the conductor, we also expect the direction of motion of that particular current to actually change. So when AB and CD are cutting the magnetic field lines, that is in the horizontal position, an EMF is therefore induced in the coil. Therefore, the current flows from A to B, then from C to D. Now, when the coil is in the vertical position, remember when AB has moved upward and DC is actually downward, that is when the coil is in the vertical position. And in that position, actually AB and DC are parallel to the magnetic field lines. That is, they are not cutting the lines of force, and therefore no EMF will be induced. So when the coil is in the vertical position, the side AB and CD are moving parallel to the magnetic lines of force, and therefore the induced EMF drops to 0 and the current stops flowing. So induced EMF drops to 0 because the conductor is not cutting the magnetic field lines at an angle of 90. So if the conductor is not cutting magnetic field lines, no EMF will actually be induced. That is why the current or the EMF actually drops to 0. Now, during the second quarter rotation, remember during the second quarter rotation, side A will actually replace D, then B will replace C, then of course D will replace A, then C will actually replace B. So during the second quarter rotation, the commutators exchange contacts at the brushes. So during the second quarter rotation, side AB moves to, that is, side AB replaces DC. So when that happens, this side AB will actually move to this side. They will move to this commutator on the left hand direction. Then when DC, at the same time, the DC will replace the side of AB. So when DC comes to this other side, it will actually be on the right hand commutator. Actually, the side AB and DC, as during the first quarter rotation, they exchange these particular commutators, or what we call the split rings. So during the second quarter rotation, the commutators exchange the contacts at the brushes. So the brushes, actually, they exchange these particular commutators. So this one moves towards this commutator, then this other conductor, it actually replaces, or it moves towards this positive commutator. So the commutators exchange the contacts at the brushes, then the coil starts cutting the lines of force, and induced EMF increases from 0 to maximum value when the coil is in the horizontal position again. So remember, now the coil is in the horizontal position with DC replacing AB and AB replacing actually DC. So we expected some current to, the direction of the current to change. However, because the commutators have exchanged, it simply means that the direction of current in the external circuit will actually remain to be in one direction because of the changing commutators. Remember, for the case of AC generators, the commutators, that is, it does not have the commutators. So in that particular case, the slip rings could not change. That is why there was a change in current in the external circuit or the external CRO. So the coil starts cutting the lines of force, and an induced EMF increases from 0 to maximum value when the coil is in the horizontal position again. So the current in the coil flows from B to A, then D to C. So because remember the side DC has replaced AB, so we expect the current to actually be moving, because it was moving from A to B, but A has been replaced by D, then B has been replaced by C. We expect the current to be moving from actually D towards C. Then of course on this side, because A has replaced D, then B has replaced C, we expect the current to be moving from B towards A, because remember here we now have B, then at point D we now have A. So the current will be moving from C towards D, then of course then from D towards the point actually C. So the current in the coil flows from B to A and then from D to C. However, because the commutators exchange the contacts at the brushes, a current in the external circuit. So the external circuit can be an external resistor or simply what we call the CRO. In the external circuit flows in the same direction. So the commutators exchange the brushes after every half a cycle. So this ensures that the direction of the induced EMF does not change. Therefore, the graph of induced EMF and the position of that particular coil will actually be in this particular manner. So remember, the current is not moving, or the induced EMF is not in the opposite direction because of the changing commutators. Unlike for the AC generator, where we had current moving in the opposite, that is in the negative side of the EMF axis. So because of the commutators, actually the current will just be in one direction, that is in the positive direction only. So that is the difference between an AC and a DC generator. Then lastly, we look at the factors affecting the magnitude of induced EMF both in an AC and in a DC generator, whereby we are saying that in both AC and DC generators, induced EMF can be increased by 1, increasing the speed of rotation of the coil. That will simply increase the rate of magnetic flux linkage, hence more EMF will be induced. The second way is by increasing the number of turns of the coil. Of course, the more the number of turns of the coil that get in contact with the magnetic field lines, the more the EMF induced. Then the third way is by increasing the strength of the magnetic field, or simply by using a stronger magnet. Then the fourth way is by winding the coil on a laminated soft iron core. Remember, the advantage of laminating the core is to reduce the eddy currents that bring about the heating effect. Then the advantage of using the soft iron core, remember soft iron is a soft magnetic material which can be easily magnetized and demagnetized. That will simply mean that it will reduce the problem of flux leakage. So in some generators, such as the bicycle dynamo, the coil usually remains stationary while the magnet rotates. So the advantage of such generators is that there are no brushes which get worn out, of course, as shown in this particular diagram. So if you can be asked to give an advantage of using a bicycle dynamo to generate electricity as compared to maybe a DC or an AC generator. So the advantage will be that AC generators and DC generators require the carbon brushes which get worn out, or they require the graphite brushes which get worn out over a given period of time. But for the case of a bicycle dynamo, it does not need any of the brushes, that is either the carbon or the graphite brushes, therefore it cannot get worn out. So this is a typical bicycle dynamo. You can see we have our magnet which is being rotated from this particular axle. Then we have, of course, the coil or our conductor here. So because this particular magnet is rotating, that means the magnetic field is meeting, or it is rotating. That means the magnetic field is meeting with the conductor at right angles. Therefore, EMF is actually being induced, and of course, that EMF is transferred to the bulb of that particular bicycle and used to light it. Remember, the rotation of the bicycle dynamo is done by the rear wheel of that particular bicycle, such that as you cycle, actually the back wheel or the rear wheel of that particular bicycle gets in contact with the axle, which starts rotating, hence rotating the magnet, which was of course positioned in such a way that as it rotates, its magnetic field lines meet with the conductor within that particular bicycle dynamo at right angles, hence inducing some EMF which is used to light maybe the bulb in that particular bicycle. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that it's okay to lose, but be careful not to lose the lessons. So the quote is reminding us to focus on the lessons whenever we fail, because that is the only way through which we can improve and be better or do better the next time we encounter that particular failure or that particular problem. Remember that every failure is an opportunity to learn something new. Therefore, true failure is when you fail to learn the lesson that that particular failure intended to teach you. And lastly, recall that the word fail simply means first attempt in learning. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you will get notified. This is our last lesson on electromagnetic induction, so expect us to start a new topic which is mains electricity in our next chapter. Until next time, this is Kind Tuition Academy. Thank you very much.